So last week we had started with work, power, energy, and we had understood the definition of work done by a force in terms of path integration. So we will pick it up from that point here. So this is session number 2 for work, power, and energy. So let's take a quick recap of what we'd learned. So we'd seen the definition of work done by a force. Okay, is defined as the path integration of f dot ds from initial to final position. Okay. So if a body is moving along some kind of a random path from some initial position, let's say over here, to a final position over here, and during that displacement there is continuously a force F acting on it. So at any instant during the displacement, if the instantaneous force vector is F and a differential displacement or a very small part of the entire displacement is ds, then the dot product of these two gives the work done during that small displacement. So for displacement ds, okay, the work done is f dot ds or f ds cos theta. So the net work done for the entire path from initial to final position that becomes the integrated sum of this, so that becomes integral f dot ds, or you can also say it is integral f ds cos theta, where theta f, these are all instantaneous quantities, so they might be changing from point to point. Okay, so for example, by the time the particle reaches here, your f might have changed both magnitude and direction. Accordingly, theta might have changed. Okay. So this was the general definition. So this is called the path integration of force with respect to displacement. So this is the word definition. Okay. Now we had also seen that if the force happens to be constant, that means it has constant magnitude and direction, both things. Okay. So it has to have both things constant. Then this definition reduces to f dot s. So it simply becomes the dot product of force and displacement. Okay. So it becomes a much simpler definition in the case of a constant force. But for variable force, that is either magnitude or direction is variable or both are variable, f dot ds is not equal to f ds, because f only is not constant. Okay. So this thing we have to keep in mind, that for variable force we cannot apply this. It is only for constant force. Okay, so let's continue ahead with an example. So we know, for example, that electrostatic force between two particles is inversely proportional to the square of the distance. So let's take an example of force like that. So a particle moving along the x-axis, okay, is under the action of a force given by the relation this, okay, where alpha is a constant and x is the particle's instantaneous x coordinate. Okay. So find the work done by this force as the particle moves from x equal to a to x equal to b. Okay. So given information is that alpha is, let us say, 50 newtons per meter square and e is equal to 5 meters, b is equal to 10 meters. So just work this question out, people. Kruti, the information above is sort of revision of what we discussed in the last week's lecture. So don't really need to write it down. You can just start with this example here. I'll scroll up after you finish this so you can take a review of that. Okay. So just start with the working out of this question. Yes, Devansh, the answer is correct. Yes, Viraj, the answer is correct. Very good. So let's just visualize the problem first. So what is happening is our particle is moving along the x-axis. Okay. From the initial position A, which is x equal to 5, to the final position B, which is x equal to 10. Okay. Now during the displacement in between, at any point, the particle has a differential displacement like this, and at that point the force acting on it is along the x-axis. So for that small displacement, the work done F dot ds. So for the net displacement, it has to be integrated from the point A to the point B. Now just replace F with the value which is given. So alpha by x square I cap, and replace the differential displacement is along the x-axis. So this becomes dx I cap. Okay. So because the particle moves along the x-axis, okay, this will only have x component, it will not have y and z component. So this becomes integration of alpha dx upon x square from x equal to 5 to x equal to 10. So it becomes a simple integration problem now. You can see A to B is like this, where you know A is equal to 5, B is equal to 10. So now you know integration of dx by x square is this. Okay. So that's minus 1 by x. So next step, see this becomes alpha into minus 1 by x from x equal to 5 to x equal to 10. So it becomes alpha into minus 1 by 10 minus of minus 1 by 5. Okay, so this is the value of work done. So make a note of this quickly. So this is an 1D example, one-dimensional example of work done by variable force. We will see two-dimensional and three-dimensional examples also, but starting off with this. Okay, people. So hope this example is clear to all of you. Now, next up, we will discuss a very standard example of a variable force, okay, which is the case of the spring force. We'll understand how to calculate work done by a spring. So this will become a standard formula for us, which will be important. Okay. So, for example, suppose we are taking the case of a spring that is along the x-axis. So the spring is, let's say, attached to a particle here, where this is the natural length position of the spring, and the spring is of constant k, and the natural length position is what we are taking as x equal to 0. Okay, so L is the natural length position, and k is the force constant of the spring in newtons per meter, obviously. Okay. Now we know that if we take the spring from this position to an extension by pulling on the block like this, if we take it to an extension so that the length extends by x, so in comparison to this x equal to 0, now this is at a positive x coordinate. So then we know that the force applied by the spring is in this direction. Okay. And the magnitude of that force we know is kx in magnitude. Okay. And along minus I cap when x is positive, when the x displacement is positive. Okay, so we can write the spring force as minus kx I cap when the displacement is plus x I cap. Now similarly we can see that if we compress the spring from its initial position, we compress the spring by pushing this like this. So some kind of external force is pushing, just like over here, some kind of external force was pulling this. Okay. So in this case, now what happens? The length of the spring is compressed to L minus x. And we can also see the coordinate of the particle has become some negative value of x. So this time, what about the spring force? The spring force is in the positive direction. Okay. So again, we can see that the spring force is along plus I cap when x is negative. Okay. So that means again the relationship between x and the spring force is the same thing, that the spring force is minus kx I cap when x is negative, or the displacement is minus x I cap. Okay, why it is minus kx? Because now the direction of the force is positive, but the x coordinate is negative. So if you see these two, you can generalize this, that in general the spring force is minus kx I cap for whatever the displacement is. Okay, for any displacement x I cap. So you can see that when x is positive, the direction of the force is negative. When x is negative, the direction of the force is positive. Yeah, so just follow it from the diagram. You know the magnitude of the spring force is kx and the direction is opposite to the displacement. Okay, so what this shows us is that the magnitude of the spring force is kx and the direction is opposite to x. So that is why when you see in the first case, what is happening here is that x is positive. So the direction of the spring force is what? Negative I cap. This is the first case. In this formula, when you substitute x as a positive quantity, you can see that this is negative of something into I cap. So the direction of the spring force is along negative x axis. It's along minus I cap. The same formula in the second case, when you take it to a negative x coordinate, like x equal to minus 5 or x equal to minus 2, this quantity becomes positive. It becomes minus kx becomes minus k into a negative quantity. So the direction of the spring force becomes what? It becomes along plus I cap. Is that clear now? Okay. So this general formula covers both the cases, whether x is positive or x is negative. It covers the situation that the magnitude of the force is kx, but the direction is always opposite to x. Okay. So now when we want to calculate the work done by the spring for any displacement, so suppose the spring is right now in a state like this. Okay. So it is applying a force like this. Okay. And now what we are doing is we are displacing the particle by very small amount dx like this. So during this displacement, what is happening? The spring force as a vector quantity is minus kx I cap. The displacement as a vector quantity is dx I cap. So the work done by the spring for that small displacement is becoming, just take the dot product, minus kx dx. So the total work done by the spring in any situation going from some initial x coordinate to some final x coordinate will become this. So it will become integration of minus kx dx from initial x coordinate to final x coordinate. So the formula for work done by a spring becomes minus half k into x final square minus x initial square. Because as you know, the integration of x dx is x square by 2. Okay. So this becomes a general formula for work done by a spring force. Okay. So we will see that irrespective of whether the spring is being compressed or extended or whatever, this formula gives us the correct answer for any situation. Okay. Yeah, so we will discuss this from the beginning. So make a note of this much first, then we'll come back to the formula for work done. Okay, so hope you understood the basic definition of, or the basic derivation of the expression for work done by a spring. So instead of doing the integration every time, we will directly use this formula. So that is why it's important that you keep this formula in mind. So now let us see the application of this in a couple of examples. So supposing we have a situation like this, that on a smooth horizontal surface, we have a block attached to a spring of constant K and natural length L. So let us say the spring constant is 20 Newton per centimeter. Initially, the spring is in a relaxed state. So x equal to 0. Okay. L is the natural length. Now, first part, if the block is pulled to the right to an extension of 5 centimeters for the spring, calculate the work done by the spring on the block. And second part, if the block is pushed to the left to a compression of 2 centimeters, okay, for the spring, okay, from initial state, not from this state, okay, from initial state at natural length. Again, calculate the work done by the spring. So let's understand this each part. So if you go by the formula based method, okay, then what is happening is in the first part, initial position of the spring is 0. Okay, it starts from natural length position. Final position will take as plus 5 centimeters because it is extension of 5 centimeters. So work done by the spring will simply be given by the formula minus half K x final square minus x initial square. So in this case it will become minus half. Now K K for the spring was given to us as 20 newtons per centimeter. So that we'll have to convert. It will become 20 into 10 raised power 2 newtons per meter into x final, which is 5 centimeters. So converted to meters square minus x initial, which is 0. So it is minus half into 2 into 25 into 10 raised power 3 minus 4 joules. So it becomes minus 2.5 joules. Okay, this is the example of the first part. Now, before you write this down, let's understand the significance of this. So what is happening here is that the block is going from this initial state where x is equal to 0 to this state where x is equal to plus 5 centimeters. But during that time, the spring force is acting like this. Okay. So it is justified that spring force is doing negative work on the block because it acts opposite to displacement. It's justified that the work done is coming out as a negative quantity finally. Okay. Right. So make a note of the question first and try to work out the second part also yourself. No, see, when you convert Newton per centimeter, it is 1 Newton per centimeter. No? So it is 1 Newton divided by 1 centimeter. So it becomes 1 Newton divided by 10 raised power minus 2 meters. So that is 10 raised power 2 newtons per meter. You learned this in Newton's laws of motion also. That 1 Newton per centimeter is 100 newtons per meter, not 1 by 100. You should remember this from Newton's laws of motion. अरे अभी तो ऊपर फॉर्मूला लिखा ना अनय. Just above we have derived the formula na, minus half k into x final square minus x initial square. So just use that formula. We just derived this formula. Work done by a spring in any situation is given by this formula. So you're just making use of that formula. I told you, no, we won't be doing the integration every time. We'll just use the direct formula. Yes, Vashist, your answer is correct. Sujal, be careful of the algebraic sign. Understand it both by formula and by logic. In second case, what should be the algebraic sign of work done by the spring? What is the direction of displacement and what is the direction of spring force? So work done should be positive or negative? Yes. Okay, so it should be work done will be negative in second case also. Devansh? Yes, Viraj, your answer is correct. Okay, now make sure you understood the working of the first part, because the second part you have to apply very similar concept. So now in the second part, you are taking it from an initial state at natural length to a final state of minus 2 centimeters. Okay, compression of 2 centimeters. Okay. Again, initially it is at natural position. Okay. So work done by spring, again just directly use the formula now. Minus half k x final square minus x initial square. So that is minus half into 20 newtons per centimeter into minus 2 centimeter whole square minus 0. So that is minus half into 20 into 10 raised power 2 newtons per meter into 2 into 10 raised power minus 2 meters whole square. So you'll get this as how much? Minus 0.4 joules. Now it's very well justified that the work done by the spring will be negative in this case also, because you're going from natural length position to a compressed state. But during that time, the spring force is acting in this direction. Okay. So you can see that work done by spring will be negative. Okay. So let's understand this with some more generalization. Okay. So when we have this formula, work done by the spring is minus half k into final position square minus initial position square. What this means that if the spring is taken from natural length position initially, so that means x initial should be 0 to any deformed state. So any deformed state means that x final is either plus x or minus x. And that is, it is either a state of extension or a state of compression, whatever be the case. Okay. The work done by the spring will be minus half k into either plus or minus of x whole square minus 0. So the work done by the spring is always negative. The work done is a negative quantity when deformed from natural state. whenever you take a spring from its natural state to a deformity, the work done by the spring will be negative as a rule. Okay. And the justification of this you've seen in the previous example. Now, similarly, if the spring is initially in a deformed state, so that means our value of x initial is either plus x or minus x. It is in a state of extension or in a state of compression, and returns to natural length t. That means our final value of x is 0. Then the work done by the spring in such a state will be 0 minus initial will be either plus or minus of x whole square. So in this case, you can see the work done by the spring will be positive. So work done by the spring is a positive quantity when the spring relaxes from a deformed state, that is x initial is plus minus x to the natural state. Okay. So if a spring is initially in a compressed state, so it's applying spring force like this, and from this it is going to a state where it's coming back to natural length. You can see that the direction of displacement is the same as the direction of the spring force. Okay. Similarly, if the spring is initially in an extended state, okay, so it's applying a force inwards, and from here it is allowed to come back to the natural length state. You can see the direction of the displacement is in the direction of the force. So in both cases, whether it is going from compression back to natural length or from extension back to natural length, the work done by spring will be a positive quantity. So a spring relaxing back from deformity to natural state does positive work. A spring going from initial state of natural length to a deformed state, it does negative work. Okay, next let us look at another example of the application of spring force formula. So now we have a vertical situation. Okay, so a block is suspended from a ceiling using a spring. So we have a spring like this which is used to suspend a block. So spring constant K, block has a mass M. So let's say the mass of the block is 5 kg, is suspended by an ideal spring. So remember, an ideal spring is massless. The spring constant is 25 Newton per centimeter. Okay. Initially, the system is in equilibrium. Now, an external agent pulls the block down through 3 centimeters, okay, and releases it from rest. So first thing is find the extension of the spring at the equilibrium position. Second, find the extension of the spring at the position when the external agent has pulled down the block. Okay, third, find the work done by the spring from the position at which the block is released by the external agent to natural length state of the spring. Okay, so from whatever position the external agent has released the block, from there back to the natural length state of the spring, what is the work done by the spring force? Okay, just work this out, people. Yes, that's correct, Prachi. First part's answer is correct. Good. Okay, so let's understand the answers for this part. So in the equilibrium position, the extension of the spring will be mg by k initially. So that is 2 centimeters. Okay. So in this position, you are taking it further down by 3 centimeters. So the total extension will have become 5 centimeters. Okay. So in this case, the work done by the spring will come from the formula minus half k into 5 centimeters square minus 0 square. So it will come according to that. So it will be minus half into 2500 into 25 into 10 raised power minus 4. Something like this, it should come out to be the work done by the spring. It should be opposite. It's going from initial position 5 centimeters to final position. Right, so these should be the answers. So let's understand this in detail. So the first part, at the equilibrium position, let's say the extension of the spring is x naught. So the weight of the block is balanced by the spring force kx naught. So the 5 kg and this is 25 newtons per centimeter. So 50 newtons divided by 25 newtons per centimeter. So here you can use this hybrid system of units because newtons will cancel out. And now in the second part, what you're doing is from this equilibrium position, you're pulling the block down by a further 3 centimeters. So now this is becoming L plus X, where from the equilibrium state, you have displaced the block down by 3 centimeters. Okay. So here X has become X naught plus the displacement downwards. So it is 5 centimeters. Okay. So for the third part, now the spring is going from this initial state where X is equal to 5 centimeters to the natural length state, X equal to 0. So during this time, the spring force will end up doing positive work on the block. Okay, so from that you will get this. To be this much. So in case you haven't done this, note this down first. Okay, so hope this is clear. Now next we will see a very interesting and important little theorem, which is the relationship between work done and kinetic energy. Okay, so it is called the work kinetic energy theorem. So the statement of the theorem is that the net work done by all external forces acting on a body or particle, whatever be the case, equals to the change in its kinetic energy. Where this net work done, this is the algebraic sum of work done by all the forces, and kinetic energy is defined as half mv square. So change in kinetic energy is half m into v final square minus v initial square. Okay. So just make a note of the theorem. We will discuss some applications and the derivation of the theorem. Is the net work done, beta? This is W net. Okay, so let us understand this in context of 1D motion. So for example, for a one dimensional displacement, suppose we have a situation like this, that a body is being acted upon by multiple forces, be it normal reaction, everything, plus some external forces, F1, F2, F3, etc. And it goes from this initial position to this kind of final position here. And in between, somewhere here, it's made a small displacement like this. So ds, okay. So let us see the work kinetic energy theorem statement. So if it had some initial velocity here, and by the time it reaches here, it has some final velocity. So net work done is equal to change in kinetic energy. Now the left hand side, the net work done should be equal to summation of work done by all the forces. Okay, that is algebraic sum of work done by all forces. Whatever forces are acting up to n. Okay, so this should become summation of F dot ds. It becomes summation of F dot ds for all the forces. Okay, because work done by any force is this. Okay, so for example, work done by the first force is integration F1 dot ds, like this. Okay, so now what we can do here is that we can take this like this. It becomes summation of, we can take the summation sign inside the integral. Okay, like this. Okay, so this is something like this, that if we say it is integral of f1 dot ds plus f2 dot ds, like this, so that can be written as integral of f1 plus f2 up to whatever dot ds. Okay, that is this step. Now summation of f for all the forces is nothing but the net force. Okay, that is the definition. F1 plus F2 plus up to whatever, that is nothing but the net. Okay, so this summation can be replaced with, so the left hand side, which is the net work done, be replaced with the net force acting on the body dot product with displacement path integral. So in the 1D case, this F net dot ds is nothing but this. Okay, where F net is equal to mass into acceleration. Okay, and you know that acceleration, which is dv by dt, can also be written as v dv by ds, no, because yeah, so you have this little trick here. So you can write this as integration of m, that is nothing but integration of mv dv from initial state to final state. Okay, so this is the proof that the left hand side, which is the net work done, ultimately comes out to be equal to the right hand side of the equation, which is the change in kinetic energy. So a lot of steps involved in this, so just make sure you understand this. So basically we are going in this sort of sense, we are saying that the net work done is summation of integral f dot ds. So that becomes summation of f dot ds. So that becomes net force dot ds. So in 1D case, that becomes just a simple product of these two because they are both in the same direction. So the net force is nothing but mass into acceleration. And then next step you replace A with V dV by ds and integrate. Okay, so this is the method of the proof of work kinetic energy theorem. Okay, so a lot of steps involved here. Carefully understand all of them and make a note, please. This dot product becomes a simple product because it's 1D. So in 1D motion, the net force is along the x-axis only, and the displacement is also along the x-axis. Okay, so Okay, so let's go over the steps again. So first thing, we are looking at the left hand side of the theorem, net work done. So it is summation of work done by all the forces. So it is summation of F dot ds for all the forces. So since ds is common over here, we just take the summation sign inside the integral. So this summation is like integration of f1 ds plus f2 ds plus f3. So we can write that as integration of f1 plus f2 plus f3, the whole thing dot ds. Now that summation of F is nothing but the net force, Newton's second law. The net force acting on a body is the vector sum of all the forces. So next step, what is happening? The summation F over here, it is getting substituted with net force. And since it's a 1D motion, so dot product of net force with displacement is the simple product. The angle between them is 0 because it's a 1D motion. Okay. So this is just becoming the magnitude of the net force into ds integration. Now magnitude of net force, Newton's second law, is mass into acceleration. So it becomes m into a into ds, and a is nothing but v dv by ds. So that's how it's becoming this. So in fact, this is like a proof of why kinetic energy is defined as half mv square. You ever wondered how that formula has come, that kinetic energy should be half mv square? That formula has come from here actually, that the net work done results in the change in the quantity half mv square. So the quantity half mv square is defined as the kinetic energy. The term half comes because of the integration. Okay. So we define kinetic energy as half mv square because of this reason, where m is in SI units in kg, v is in meters per second, so kinetic energy is in joules. So what you can see, that 1 joule is equal to 1 kilogram meters square per second square, which is the same thing as 1 Newton meter. Okay, so work done and energy, they share the same unit and dimensions. Okay, so let us look at an example of the application of this. Now what we have here is, let us say, a spring mass system, but on a rough surface. So we have this situation. Okay. So given the mass of the block is, let us say, 1 kilogram, take g as 10 meters per second square. The coefficient of friction is 0.2 and the spring constant is 5 Newton per centimeter. Okay. Now initially the block is held at rest with an external force acting on it for x naught equal to, let us say, 1 centimeter extension of the spring. Now suddenly the external force is withdrawn. So find the speed of the block at the instant when the spring is at natural length position. Okay. So the moment you release this external force, you can see that the spring force, when you calculate here, you'll see that the spring force exceeds the frictional force that the block can have acting on it. Okay. So the spring force is going to exceed the maximum friction, which means the block will accelerate towards the left. But you realize that as it accelerates towards the left, the net force acting on it is variable because there's spring force involved. So it will have a variable acceleration. So it's not so easy to calculate the speed from kinematics. You'll have to deal with the variable acceleration integration situation. But on the other hand, if you use work kinetic energy theorem, here you can come up with a very easy solution. Okay. So hint to you is use work kinetic energy theorem. That will be much easier compared to integrating the variable acceleration. I hope the point of the question is clear to all of you. The moment you release the external force, there is a net force acting towards the left because the spring force will be greater than the frictional force. But that force will vary as the block moves because the spring force is a variable force. So rather than use Newton's laws to find acceleration and then kinematics to find velocity, it's much easier to use directly the work kinetic energy theorem. Okay, so let us complete the calculation for this. So what you can see here is that the block is going from an initial state of this to a final state. Now here the initial speed is 0 to a final state where it's at natural length position. So the net displacement of the block that will be in this direction, and its magnitude will be x naught. Okay. But during this displacement at any in between point of time, when this is the state, x is in between 0 and x naught, the forces acting on it are spring force, okay, mg, normal reaction, and kinetic friction. So you need to understand that normal reaction will be equal to the weight. So kinetic friction, which is mu n, will become mu mg. Okay. So the weight of the block is 10 newtons. So the kinetic friction will become 2 newtons. So that's one thing we understand. And x naught was 1 centimeter, and the spring constant was 5 newtons per centimeter. Okay, so initially you can see when you release it here, it has an acceleration like this. So that's why by the time it reaches here, it's got some velocity which we want to find out. So now we'll just apply work kinetic energy theorem. So according to that theorem, the net work done should be equal to the change in kinetic energy. Okay, so the net work done here will be the work done by spring plus work done by friction plus work done by normal reaction plus work done by mg. But these two are not required actually. Work done by normal reaction is 0, work done by mg is 0 because displacement is perpendicular to force in these two cases. Okay, work done by friction, we can just write it as this, so it is minus of F into S. So it is minus of friction was 2 newtons multiplied by the displacement was 5 centimeters. Okay. So it is minus 0.1 joules. This is the work done by friction. Now the only thing remaining is the work done by the spring, which is a variable force. So we cannot use dot product. For the spring, we will use the formula. Yes, yes. Now work done by spring will be negative. Sorry, work done by friction will be negative. Work done by spring will be positive. So for work done by spring, we will use the regular formula. It is minus half k x final square minus x initial square. Now this is the final state. So in the final state, x final is 0 because you're back to natural length. Whereas the initial state, x initial was plus x naught. Okay. So this becomes minus half k 0 minus x naught square. So the work done by the spring is this much. So it is half of spring constant, that's 5 Newton per centimeter. So 500 newtons per meter into x naught, which was 1 centimeter. So this much. Okay. So it is 5 by 2 into 10 raised power minus 2, is it? So it is hmm. So wait a minute. What we'll do here is, see, the fact that we'll get the net work done as a negative quantity, that means the block will never reach the natural length position. It will come to rest somewhere before. Okay. So we have to give it a bit more of. So let's reduce the friction coefficient. Okay. Otherwise, this question will not make sense. So let's change the coefficient of friction to this much. Let's change the coefficient of friction. So just make a change in the, or let's do one thing. Let's keep the coefficient of friction the same. Let's change the spring constant. So let's make the spring constant larger. Let's make it 20 Newton per centimeter. Okay, so just make a correction with the spring constant. Okay, change it to 20 Newton per centimeter. Okay, so I'm making this 20 Newton per centimeter. This will become how much now? This will become 0.1 joule. And because we converted this from, okay, so we have taken the spring constant. In this case, we are taking it as 20 Newton per centimeter. So when you convert to Newton per meter, you have to multiply by a factor of 10 raised power 2. Na? So that's how we get this. Okay. So in fact, let's do one thing. Let's change it to 25 instead of 20 even. Let's change this to 25 newtons per centimeter. All right. So this will give us 25 by 2 into 10 raised power minus 2. So plus 0.125 joules. This is the work done by the spring. This is the work done by friction, and the other two are doing zero work. So left hand side of the equation, the net work done, that will be equal to how much? Minus zero point 0.1 plus 0.125. So it will be positive of 0.025 joules, or 2.5 into 10 raised power minus 2 joules. This is the net work done. So this will become the kinetic energy. Okay. So now right hand side of the equation, the change in kinetic energy, that is just half mv square minus 0, because initially the block was at rest. So we have half mv square is equal to this many joules. Okay. Block's mass was 1 kg. Okay. So v square is 5 into 10 raised power minus 2. So v will become root 5 into 10 raised power minus 1 meters per second. This will be the speed of the block. Root 5 by 10, that's correct. Okay, so anyway, whatever the final answer, the important thing is that we are able to solve this problem very easily by just using the formula for work done by spring, and work done by friction, very easy. It is nothing but minus of friction into the displacement, because friction is acting opposite to displacement and the magnitude of friction is constant. Okay. So yeah, the first situation where we had taken the spring constant was 5 Newton per centimeter. So what was happening in that case was we didn't have enough spring force to bring it to the natural length position. The block would have stopped somewhere before it came back to the natural length position, because the kinetic energy was becoming zero before x equal to 0. Okay, so there's nothing wrong with that. That situation can also happen, but we would not get an answer corresponding to what this question has asked. This question wants the block to come back to equilibrium position. So for that we need a stronger spring constant. So we have changed the spring constant from 5 Newton per centimeter to 25 Newton per centimeter, so that we get some logical answer for that. Okay. So anyway, so this is the end of today's lecture. So the important learning here is the work kinetic energy theorem, and before that the work done by spring formula, okay, which comes from integration of f dot ds method. But once we have developed the formula, you are not supposed to do the integration in every question. Instead you are supposed to use the direct formula which we have discussed over here. Okay. So make sure you go through today's lecture notes very carefully. I will send you a list of questions to do from HC Verma as well as a worksheet, and make sure you revise the lecture notes and the derivation very carefully before starting the questions. So that's it for today's lecture.